Earth is a Nuclear Planet, Chapter 4, A Fate Worse Than Global Warming. Some environmentalists have such a profound distaste for nuclear energy that they categorically dismiss the subject without further discussion. This is unhelpful to say the least, especially given nuclear's excellent record of performance and safety. The accidents at Fukushima and 3 Mile Island killed no one, and no one will ever build a reactor like Chernobyl again. And yet, some people seem almost stubbornly afraid of nuclear power. It's like writing off every automobile that's ever been built or ever will be built because some Ford Pinto gas tanks blew up a half-century ago. Chernobyl was the Pinto of nuclear reactors. As renowned green journalist George Monbiot wrote in the Guardian newspaper just days after Fukushima, quote, "While nuclear causes calamities when it goes wrong, coal causes calamities when it goes right. And coal goes right a lot more often than nuclear goes wrong." End quote. This perspective doesn't seem to matter to some people, but it should, because the actual harm caused by the production of nuclear power is nearly non-existent. After 65 years, with about 100 reactors operating in the U.S., and another 100 or so at sea, only 16 deaths have been attributed to the production of American nuclear power. 3 operators perished from the partial meltdown of an experimental reactor at Idaho National Laboratory in 1961. 10 additional deaths came from construction accidents at various commercial power plants. And there have been 3 deaths and 1 severe injury in the U.S. fuel enrichment and processing industry. So after generating about 27 trillion kilowatt hours of clean electric energy over the last several decades, which equals to 29 years of electricity for all U.S. single-family homes, not a single member of the American public has been injured or killed by the production of nuclear power or by spent nuclear fuel. By health and safety statistics, an operating nuclear power plant is one of the safest work environments in the entire country. And as it turns out, the elevated leukemia rates found near some nuclear plants, formerly blamed on radiation, have now been linked to other industries, both past and present, in the same industrial zone. The fact is, nuclear power is so safe that a person in the United States actually has a greater statistical chance of being shot by their own dog than being harmed by either nuclear power or nuclear waste. Amazing, but true. About 1 American each year gets shot by their own dog. Allowing for population growth and recent gun proliferation, we can guesstimate that there have been roughly 35 dog-involved shootings in the U.S. since the advent of commercial nuclear power in 1957. Compare that to the casualties I cited earlier. But even if we do accept nuclear's stellar safety record, what about the mining? Section 4.1, Digging Deep. There was a substantial number of cancers and mortalities in the early days of U.S. uranium mining and milling, most of which took place in the Navajo Nation with local labor. At the time, cigarette smoking was common, and safety regulations were either lax or non-existent. As it turns out, inhalation of mining dust and high levels of radon gas, which decays into the same radioactive plutonium found in cigarette smoke, were contributing factors at any type of underground metal mining, not just uranium digs. The arms race against the Soviets and the systemic neglect of indigenous American health and safety made the situation even worse. Wind-blown dust from abandoned mine tailings and waste rock may well have caused cancers and shortened lives, and leaching chemicals from in situ mining were not always properly monitored, which polluted local aquifers. Notice the monitor well shown in Figure 23 on the website. As regulations and oversight improved, ventilation and respirators were introduced to deep-shaft uranium mining. Casualty rates soon reduced to the same levels found in other metal mining operations. Canada mines far more uranium than the U.S., and a major study has shown that the health of their miners is on par with their American counterparts. And just how healthy are their miners? A recent report put it this way, quote, "There has been no known case of illness caused by radiation among uranium miners in Australia or Canada," end quote. Another Canadian study showed that the CO2 released by uranium mining and milling amounts to just 1.1 grams per kilowatt hour of electricity produced from the resulting fuel. When power plant construction, O&M, operations and maintenance, and decommissioning are factored in, nuclear power's total life cycle carbon emissions are only 6 grams per kilowatt hour. Compare this to a whopping 380 grams per kilowatt hour emitted by heavy coal-burning countries like Germany. And this was before Russia invaded Ukraine. 8 months later, in November 2022, anti-nuclear Germany was up to 459 grams of CO2 equivalent emissions and facing the onset of winter. As we show in Figure 22 on the website, nuclear has the lowest greenhouse gas emissions of any clean energy technology. Nuclear's already meager emissions can be further reduced to nearly zero with electrically powered equipment for mining, milling, and construction, energized by a nuclear-powered grid or an on-site microreactor. Even so, the total environmental impact of an energy system comes from more than its carbon emissions. The resources consumed in building, fueling, operating, maintaining, and decommissioning the system must also be taken into account, along with the mining to produce said resources. The essential question is this: what is the total footprint of an energy system compared to the total energy derived from that system? Throughput is engineering speak for the resource consumption of a system. Conventional power plants consume fuel as they operate, but they also consume a variety of other material for extended periods of time. Construction components like steel and concrete are typically amortized over the productive life of the plant. The steel throughput of a power plant, for example, is the quantity of steel used relative to the energy produced by the plant. If 70 tons of steel are used to build a nuclear plant with a yearly output of 1 terawatt hour and an estimated lifespan of 60 years, the plant has a steel throughput of about 1.17 tons per terawatt hours. Doing the math on this, 70 divided by 60 equals 1.166. But caution is strongly advised. Relying on this popular metric can sometimes be awfully misleading, because any throughput calculation is only a snapshot. As technologies evolve, they often reduce their material throughput, sometimes dramatically. For example, engineers now have the technology to make a reactor last for 80 years or more, doubling the original 40-year estimated lifespan. This doubling cuts the steel throughput of a nuclear plant in half, which dramatically alters any quantitative analysis. Since doubling the life of a reactor effectively doubles the life of the plant, the throughput calculations for copper, concrete, glass, aluminum, and other materials used in building the plant will reduce as well. Nerd note: the metal walls of a reactor pressure vessel, or RPV, become embrittled over the years as the zooming neutrons in the core bury themselves in the metal walls of the RPV. Through physics wizardry, some metals will slowly transform into wall-weakening elements, such as helium-4, iron-56, and other pesky isotopes. Over the years, these insults eventually degrade the metal's crystalline structure, making the vessel susceptible to microscopic cracks. Since this is a well-known issue, operators conduct embrittlement inspections during each refueling cycle. Luckily, a reactor vessel's metal crystalline structure can be restored by annealing the metal. To do this, the emptied vessel is heated at 550 degrees Celsius for about 200 hours, then slowly allowed to cool. This repairs the crystalline structure of the metal, even after years of neutron bombardment. Large RPVs can be annealed in place with induction heaters. The Russians are already doing this. The RPVs, or small modular reactors, will be taken back to the factory for annealing, refueling, and other maintenance. Since high-temperature Generation 4 systems like the molten salt reactor will operate well above 550 degrees C, the tantalizing possibility exists that MSRs, or molten salt reactors, will be continuously self-annealing, enabling service lives of well more than a century. They should have fusion figured out by then. Energy generation requires mining for two different things: the material for building the plant and the material to make the fuel. In contrast, passive energy harvesting technologies like wind and solar do not require fuel. Wind and sunshine are not fuels. We'll talk about that in Chapter 7. Nuclear power takes the extra step of excavating deep geologic repositories, or DGRs, for the long-term storage of used reactor fuel. Of course, the mining for this must be considered as well. Currently, nuclear must dig for its fuel, while renewables obviously do not. Their quote-unquote fuel comes to them free of charge and with no mining karma attached, which is nice work if you can get it. About 90% of the uranium for U.S. reactors is mined and processed outside the country, where ore concentrations are typically higher. Nowadays, most uranium miners don't even go underground. This partially stems from advances in automation, and partially because 57% of the world's uranium, and virtually all uranium mined in the U.S., is now being extracted by in situ leaching, or ISL. This simple process injects a leaching solution into an underground uranium deposit, either a sodium carbonate mixture, basically washing soda, or a dilute vinegar-strength sulfuric acid, depending on the chemistry of the ore body. Pumps draw up the dissolved uranium, which is then piped to an on-site mill, where the slurry is dried and filtered. One nice thing about in situ leaching is that it doesn't generate waste rock and leaves almost no tailings, the final waste material of any dirt mining process. Some copper mines also use ISL, but most copper is extracted either through deep shaft or open pit mining, and renewables use a lot of copper. But whether a mineral-bearing ore is scraped from the surface, or brought up to the surface, or left where it is in situ and leached of its desired mineral, the same chemicals are used to leach uranium and copper from their respective ore. Whether it's a uranium mine or a copper mine, the mineral-bearing ore is ground into rubble and milled into a sand or powder, then the material is piled in heaps and sprinkled with an alkaline or acid wash, depending on the ore chemistry. The so-called pregnant liquor is collected from below and processed to remove the leached-out metal. Finally, the depleted liquor is sent to a tailings pond where it dries to a solid. Section 4.2, Dirt Mining. The 43% of mined global uranium that is not recovered by in situ leaching is mined by either underground or open-pit methods. We have estimated that the combined global average waste-to-ore ratio for uranium dirt mining is about 3.9 to 1. This means that for every ton of uranium-bearing ore dug from the earth, about 3.9 tons of waste rock will be displaced as well. We encourage you to take a look at our mining supplement at the back of the book. In open-pit mines, this is called the strip ratio. The only real difference between open-pit mining and underground mining is whether the ore body is close to the surface or deep underground. But once the ore is accessed, the process is the same. The ore-bearing raw material is excavated, waste rock and all, and sent to the mill for processing. Once the mill extracts the mineral from the ore, the depleted ore is considered waste rock as well. Although, when prices rise, depleted ore tailings are a top candidate for re-leaching. Since the leaching process is imperfect, there will always be a bit more uranium that can still be extracted from the rubble and dust of an evaporated waste pond for the right market price. Ore concentrations will vary from mine to mine. Some of the world's best uranium deposits have ore concentrations of 0.5% or higher, but most mines have significantly lower values. We show in our mining supplement that the world's average uranium ore concentrations, often called the ore grade, at today's mines is a paltry 0.078%. Now, you don't need to be a uranium prospector to know that this means some mighty slim pickings. For every kilogram of uranium-bearing ore dug out of the earth, chances are that only about 0.078% of each kilogram, or 78 grams, will be uranium oxide. A comprehensive assessment of any system's environmental footprint would have to consider the total material dug out of the earth in order to build, operate, and maintain the system. This includes the waste rock, the mineral-bearing ore within the waste rock, and the finished material or refined mineral derived from that ore, steel, copper, etc. The recycling of finished material must also be taken into account, as this can significantly reduce the mining and milling footprint. Only 43% of global uranium is obtained from dirt mining, while 57% comes from in situ leaching. While the finished material throughput for nuclear is tiny compared to other energy technologies, nuclear's raw material throughput can be substantial due to the volume of waste rock dug up by the 43% of global uranium production. Aside from digging into the numbers on uranium, we also consider the raw material or displaced earth behind the other finished materials needed to build and maintain nuclear, wind, and solar energy systems. This is covered in Part 2 of our supplement. For some perspective on this, the global rock-to-metal ratio, or RMR, of elemental iron, from which steel is made, is 9:1. That is, for every ton of iron-bearing ore, 9 tons of waste rock are typically exhumed as well. Here's some more fun mining facts. The rock-to-cement ratio is about 1.6:1. Rock-to-cement to concrete is about 1.1:1. Rock to aluminum is about 7:1. Rock to chromium is about 18:1. Rock to zinc is about 71:1. Rock to copper is about 513:1. Rock to uranium is about 3,000:1. And rock to fuel pellets is about 21,700:1. These last two numbers are clearly a problem, especially for a massive and long-term build-out of nuclear power fueled by freshly mined uranium. But as karma would have it, there are several alternative sources for reactor fuel which can greatly reduce and potentially eliminate any future need to displace more raw material to make even more fresh fuel pellets. We'll explore these game-changing options in the next 2 chapters. To be entirely candid, it will be difficult for existing nuclear technology to build out big enough and fast enough and do the job it can plainly do so long as it continues to rely upon business-as-usual uranium mining for its fuel supply. The first automobiles were built by hand, but things had to change to put the world behind the wheel. Sources and methods must change as well for the build-out of nuclear power. For an in-depth discussion of where uranium mining sits at present, we invite you to dig through our mining supplement. But as you explore the numbers, keep in mind that they are only a snapshot of existing conditions. Methods can and will change bigly in the years to come. The legacy of uranium dirt mining leaves little to be proud of. But things have changed. Stringent regulations now ensure that existing and future uranium digs must set aside sufficient funds for land rehabilitation. The former Mary Kathleen mine in Australia, for example, is now an operating cattle station with unrestricted access. In Kazakhstan, where the world gets nearly 40% of its uranium, virtually all uranium mining is now done by in situ leaching. The same holds true for every uranium mine in the United States, most of those in Uzbekistan, and some in Russia as well. Most of the uranium dirt mining that is still being done in the world is taking place in Canada and Australia, where mine rehabilitation is strictly enforced. Much of the rest is happening in Namibia and Niger, where China has been scooping up underperforming mines. Digging for fuel does not have to leave a scarred landscape. Unlike coal mining, in which half or more of the exhumed material is carted away and burned, uranium mines have plenty of waste rock to fill whatever hole they dig. That's because the recovered uranium will often average just 0.078 of the total displaced Earth, less than 0.1%. At a properly managed uranium mine, displaced Earth becomes replaced Earth. Once the mine is played out, the hole is filled, and the land is rehabilitated for future use. This approach even passes muster in anti-nuclear Australia, where they're grazing cattle atop a rehabilitated uranium mine. Ironically, nuclear fear helps to ensure this happy outcome. Unlike iron and copper mines, where rehabilitation may not be strictly enforced, the onus on uranium has inspired both locals and environmentalists around the world to pay very close attention to the rehabilitation of any uranium dig, even though the rubble at a granite quarry can be as radioactive as uranium mine tailings. The good news is that the mining footprint of nuclear fuel can be reduced to virtually zero with existing and emerging technology. This will come in handy because, as we show in Roadmap to Nowhere, the U.S. may need about 1,800 gigawatts of nuclear power to supply all primary energy by 2050. Meaning all forms of energy, not just electricity. The country now has about 95 gigawatts of nuclear up and running, so a national nuclear grid would amount to a 20-fold increase. That means 20 times the fuel, but it does not necessarily mean 20 times the mining. With the alternative sources and methods discussed in the next few chapters, both a national and global build-out of nuclear power would be entirely feasible and sustainable, with an environmental footprint a mere fraction of what renewables could ever hope to achieve, even with dirt-cheap, grid-scale batteries. By mid-century, the throughput for nuclear power could be a mere fraction of what it is now for renewables. Check out Figure 25 on the website for an eye-popping graphic on this. It isn't even close.